Hi guys, today we are going to review few methods that are required for designing the digital control system. Such method involves the frequency design based method, and few involves the root locus method. Now we will go through the series of method in this video tutorial, and I hope so that you will really enjoy. Now, first of all, let's take a recap about what we have done before the mid exams. In this chapter 4, we first of all studied the mapping of the S plane, Z plane. After that, we also reviewed how the variation in the S plane will cause an impact in the Z domain. I hope so that you do remember the how we trace those primary and secondary strips, and while moving along those strips, what were the impacts in the Z domain as well. So based upon all those facts, now let us just begin to study that how we can design a system that will be making the frequency response method. I hope so that you are familiar with the network analysis subject, in which you perform the AC analysis over the system, and with the help of that response you actually observe that by varying the frequency what is the impact on the output of the system. Fine. While doing that, you actually plot the figure that was based upon the body plots, and you actually measured the two things. One was the magnitude and other one was the phase. Similarly, in this lecture, we will be getting the familiarity with both those magnitudes and the phase. Now, in doing so, first of all, we will try our best to find out the input response with respect to sinusoidal input, and for that purpose we will be performing the impulse transfer function, and all those z transformation over the input. Okay, fine. uh, Before moving ahead, you must know that design based upon the frequency response will be very useful while you are actually designing the compensator. Either you want to compensate your output with respect to the leading mechanism or the lagging effects and all those things. You must have the deep knowledge regarding the frequency responses. Okay. Also, you must place a low pass filter before the sampler so that you can filter out your selected sidebands, which will be based upon the low pass filter, and they must be corresponding to the low frequencies. Fine. Okay. Now let's just consider this system, um, which is by default set to be a stable system, and we are actually providing it with the sinusoidal input, and after that there is some sampler. I hope so that you are familiar with it, and we need to find out the output response of the system with respect to the sinusoidal input. Keep in mind that before this tutorial you were actually finding out the response with respect to the unit step input, as well as in your exam you were also provided with to find out the response with respect to the velocity input signal as well. Now let us just confine ourselves, and let's just find out the z transform of the sinusoidal input. Okay. Now first of all, we just put u of t and replace that thing with u of kt, because we are going to discretize it. And similarly, the sign of omega t has also been replaced with sign of k omega t, where k is the sample starting from 0 to onward. After that, we just applied the z transform theorem. You can also find the z transform of sine input with the table as presented in your chapter 1. And after that, you just multiply this input with your stable system g of z in order to get the output y of kt, or you must say x of kt, because here it is being defined as x of kt. Now the question is that why are we doing such kind of all calculations regarding finding the frequencies, phase, and all the magnitude, what we are concerned with. Actually, when we excite the system with the help of the sinusoidal input, we have two variables that can be used to extract the information. One is the magnitude, that is concerning the amplitude of the signal, and other one is the phase. Now, since you have used the low pass filter, the output frequency will be preserved. You cannot do alteration in it unless or until you are define it from the input side. But what you actually get from that the input is the two things. One will be the magnitude and other one will be the phase, which is multiplied, or you can say in time domain you actually convolute it with your system. So so let's just find out the output signal of this discrete time system, and in other words, let's just find out the response of the system in terms of magnitude as well as phase. Now in this equation, you can easily observe that your system g of z is multiplied with the z transformed input signal, and you can easily simplify it by resolving this term into its partial fraction just by a over z something plus b over z something and so on. By doing that, you can easily observe the two coefficient a and a dash just according to your book, and plus the terms that will be involved by your system g of z. If your system g of z is just a 1, which is a constant, this whole term will be just replicated by 1. So let's just try to find out the values of the coefficients a and a dash. For this purpose, we just multiply the denominator of the left hand side with the factors on the right hand side of this equation, and we get the following result as a of z into z minus e raised power minus j omega t plus the second term, and this term is indicating the if there is any of the g of z involved in the system. Now, but just by using the conventional methods in order to obtain the factors values a and a dash, I just put one of the root equal to z is equal to e raised to power j omega t, and by solving it, I get the value of the first coefficient factor, that is a, that is equal to g into the system that was replaced by this identity over 2j. Now, similarly, we can also find out the value of the second factor a dash by just placing the roots of the respectable um, factor and substituting it into the main equation, and in this way we can also find the second coefficient a dash. Now you can easily realize that this quantity g of ej, which is a Euler identity, and we have written the system g of z in term of its Euler quantity, which is just equal to the magnitude and the phase as represented in the following equation. Since there were two quantities, one was g of minus j omega t and other one was with positive quantity, so we can just replace those things with the variation in their phases. One will be the negative and other one will be the positive. However, the magnitude in both the cases will remain same. Now let us just replace all the factors of this equation in the previous slide in order to obtain the x of z in the general manner. This is the final equation that is all be represented in the form of a phase and the magnitude. Now if you take the inverse z transform, you can easily find out the uh, steady state response of the whole system. And also keep in mind that if there are transient in the system, all those transients will be eliminated at the steady state. Therefore, if I write this whole equation in the form of inverse of x of kt, which is a discrete time system, at the steady state, this quantity that are being the transient involved with respect to the g of z system will be eliminated, and only the final impact of this input will be left behind. Now, what does 4.36 equation implies? It just implies that the whole system is written in the form of the magnitude m, which is the gain of the discrete time system, and when it is only subjected to your sinusoidal input, and the other factor is the phase. Now, finally, we can conclude that if you want to find out the response of the discrete time system in terms of its frequencies, you just need to substitute z equal to e j omega t. In this way, the function is only commonly called as sinusoidal pulse transfer function. And also note that the system is periodic in nature, and it will be repeating after regular interval of time instant. Now let's just apply the concept of the topic that have been uh, discussed before, in which you need to design the system that is based upon the frequency response method. Now in this previous slide, you have studied that we need to define the magnitude and the phase that are responsible for obtaining the information if the signal at the input is sinusoidal. Now let's just consider this example 4.10, in which you need to consider the system defined by xkt, that is equal to ukt plus ax into k minus 1 into t, where t is the sampling time and u of kt is the input signal and xkt is the output. You need to find out the steady state output xkt when the input u of kt is the sampled sinusoidal, and it's defined by a sine k omega t. So let's just apply the z transform in this on the signal, and we just marked over here that u of z is the z transform of the input signal, x of z is the z transform of the output, and from this point that k minus 1, we apply the property as defined in chapter 1, and the delayed property, that's a into z inverse x of z, right? Now let's just define the impulse transfer function xz or uz, that's equal to 1 over 1 minus a into z inverse. Now if you want to find out the steady state of the output x k of t with the input defined is the sinusoidal, you just need to replace the z with e raised to power j omega t, as we have discussed in this slide number 7, that if you need to find out the response of the system based upon the frequency response, where you have defined the input to be sinusoidal, you just need to find out first of all the impulse transfer function in the form of z, and just replace that z with e j omega t into the system. Now you can see easily here that g of z is being replaced with g of e j omega t, that is equal to now 1 over 1 minus a into e raised to power minus j omega t. And you know that the e j omega t is just the Euler property. By defining it, it's equal to cos theta plus j into minus sine theta, where theta is equal to omega t. Fine. Now you need to define your steady state output equation x of s. In the slide number 6, where you have defined the equation 4.36, it states that x of kt is steady state. It's actually equal to the magnitude m divided by 2j into sine of k omega t plus theta. Now it's been clear that you require only two quantities in your equation. One is the phase and other one is the information of the magnitude. Now let's just again return to the example. Now after simplifying it, we can find out the magnitude of this whole system just by amplitude is equal to m, that is equal to the mod of the system that we require. That means that 1 over the square of the real terms plus the square of the imaginary terms and take the square root of the whole. This will give you the overall magnitude of the system. Now keep in mind that if there is any factor, real and the imaginary, and the numerator as well, you need to define the same process for the square of the real and the imaginary term in the numerator as well. Now since there is nothing in the numerator, so you will go for this just the simple version by just applying the property of determining the magnitude. Now next, the last step is to determine the phase. It's simply equal to tan inverse of the y over x term. Now here the y term is a sine omega t and the x term is 1 minus a into cos omega t. You just divide it and you will get the information of the phase. Now in the end you can finally substitute the values of the magnitude and the phase into this steady state equation, and here you go. Now, the next topic is the bilinear transformation and the omega plane. Now, before we implement the frequency response analysis to design our discrete time control system, there are some modifications. If we apply the frequency response in Z plane, then we will not be able to apply it directly because the simplicity of the Z plane will be lost. Thus, we cannot implement the frequency response to the Z-plane directly. Also, the Z transformation maps the primary and the complementary strips of the left half plane of S-plane inside the unit circle of the Z-plane. However, the conventional frequency response do not apply to the Z-plane. Now this difficulty has been overcome by introducing another plane that is known as the omega plane and transforming the Z plane into the omega plane. This is called the bilinear transformation or or omega transformation. Now this bilinear transformation has already been discussed in the class in the section 4.3 where we were checking the stability analysis by using the bilinear transformation and the routes table. The only difference is that in that equation we were not considering the sampling time and it was assumed to be unity. However, in this section we are completely defining the bilinear transformation in terms of its complete model that is actually depicting the Z domain and relating it with the omega plane. Now let's just transform this equation of bilinear in terms of the omega and we get the omega is equal to 2 over t into z minus 1 divided by z plus 1, and here the t is the sampling time. Now let us do some mapping between the S plane, Z plane and the omega plane. Now in this slide I will tell you that how we actually map the Z plane and with respect to the omega plane as well as with respect to the S plane. Now as you can see that all the entire left side of the S plane is being mapped inside the unit circle of the Z plane, And also keep in mind that we are considering the primary strip at this point, and also all the corresponding left half plane is being marked in the same manner of the left side of the omega plane. Now let's just observe the origin of the unit circle at the point C is marked at the point -2 by t at point C in the omega plane, and it's been marked at the infinity of the S plane. Now note that as we move from point 0 to j omega s by 2 on the S plane, that is from point A to B, we actually move from point A to B, that is from 1 to -1 in Z plane, and in the omega plane we move from point A to B along the imaginary axis, that is from point 0 to plus infinite. And it's also clear that the S plane movement from A to B is similar to that of the omega plane, but only difference is that we have moved only a primary strip in S plane from 0 to omega s by 2 along the imaginary axis, but in the omega plane we have taken step from 0 to plus infinite along the imaginary axis. Now you can see from the figure between the S plane and the omega plane, it's clear that the S plane is similar to that of the omega plane, but only the main difference between the S plane and the omega plane is that if you are moving in the primary strip from 0 to omega s by 2, or in the negative axis omega s by 2 along the imaginary axis in S plane, you will be taking the movement between minus infinite, that is at the point D, towards the positive infinite at the point B in the omega axis along the imaginary axis, omega plane actually. Now once the pulse transfer function g of z is transformed into g of omega by means of omega transformation, it may be treated as conventional transfer function in omega plane. Conventional frequency response techniques can then be used in the omega plane, and so we can establish the frequency response design techniques that will be applied to the design of the discrete time control system, and they will both be treated in the same manner. But once you have transformed the z plane into omega plane, now you will take the omega plane as a reference. Now let's just introduce the fictitious frequency represented by V and introduce it into our obtained frequency response omega. Since we need to draw the board diagram for the transfer function in omega, so we will be replacing the desired frequency with our own fictitious frequency in order to evaluate the whole system in terms of its board diagram. So what we do, we just place and replace the omega with j of v in the frequency plane, and correspond it similarly in the z plane by just entering the z equal to j omega t, as we have studied in the previous slides, that how we actually correspond those frequencies with our z plane and with respect to the s plane. So just by doing this we actually obtain the 2 by t e j omega t minus 1 divided by e j omega t plus 1. Now just do some rationalize to this function, and so that we can enclose the whole bilinear transformation into some sine or cosine function, and by simplifying it we obtain the 2 by t j tan into omega t by 2. Now this is the relationship that is telling us the relationship between our fictitious frequency and relating it with that of the original frequency response. And you know that this frequency response can be easily coordinated with the z plane as well, and so on. So you can move between your fictitious desired frequency and your s plane and your z plane and your desired actual frequency response in the similar way, and so back and forth. Now let's just consider the example 4.11, in which we are going to apply the concept of bilinear transformation. Now consider the transfer function system as shown in the figure 4.34 with sampling time 0.1 second, and we are going to apply the concept of the bilinear transformation over to the system. And first of all, we will just obtain the g of z, and next we will transform that z into omega plane. And you can also see the relationship between the actual frequency and the fictitious frequency along the y-axis. And just now, since it's a cascaded system, we'll just multiply it in the frequency domain and apply the z transformation theorem and obtain the g of z as 0.6321 divided by z minus 0.367. Now we're using the fact from the equation 4.37, where the relationship was defined by the z and the omega as 1 plus t by 2 omega divided by 1 minus t by 2 omega. By substituting the value of the sampling time as 0.1, we obtain the 1 plus 0.05 omega divided by 1 minus 0.05 omega. Replacing this g of z system with this value of the z, we can easily move into the omega plane, as g omega is equal to 0.6321 divided by 1 plus 0.05 omega divided by 1 minus 0.05 omega minus 0.3679, and just do the simplification over here. Now if you compare both the systems in the S plane and the omega plane, you can easily see that the gain of the plant is 10. However, in omega plane it's approximately 9.24. Similarly, the plant has a pole S at S is equal to minus 10, whereas in omega domain it's actually equal to minus 9.24. Although both of the systems are almost similar, but there is a one major difference, that the plant is not having a zero, whereas in the omega domain there is a zero at this location, 1 minus 0.05 omega. So now if I simplify this zero and write it as the domain omega is equal to 2 by t, and by substituting the value of t as 0.1, it can be seen that omega is equal to 20. Now if I approach this t to what the minimum value, let's say it's become 0 by some reasons, the 0 will reach towards the infinite. Now let's just conclude the whole discussion, that we said that the omega and the S plane are nearly similar, and if that is true, now let's just apply the final value theorem. And now let's just conclude the whole discussion by stating that the S and the omega plane are almost both similar. Now if that is true, then if the omega and the S both approach to 0, their result should be similar. Now if we see that, now in the left side of the equation, where limit is applied to the g omega, where omega is approaching to 0, you can easily see that this term will become 1. Now if the limit when applied to the S plane where S approaches to 0, you can also see that this term will become 1. Now it is clear that by using this fact we can check the numericals, that whether we have transformed the system in the omega plane using the bilinear transformation theorem, is it correct or not. If it is correct, then S and the omega plane will both give the same result by using this whole equation and the limit theorem. So now let us just finally conclude the whole discussion by writing the impulse transfer function for g of z and g of omega, and this g of z can easily be transformed into g omega by just inserting the equation of the bilinear transformation as we have discussed in previous slides. And here the beta naught beta 1 and alpha naught alpha 1 are just the constants similar to those of the b0 b1 and a1 and so on. These are all the constants. So I hope so that you have easily understand the concept of the S plane, Z plane, and the omega plane, and hope so that you have also understood this design method using the frequency response. And if you have any question regarding this lecture, you can easily email me, and the email has been just placed in your drive, so you can easily coordinate me, and soon this lecture will also be available in your drive as well, and hope so that you will enjoy. Thank you. Have a nice day.